Good. Let's start sharing the screen as well. Here you go. What I want to show you here is the syllabus, the schedule of the syllabus. We are writing here. I hope to finish vectors today and maybe starting 2D motion even today. Let's see how it goes. But what I want to point out is the exam. Exam is going to be in 9 days, next week on Wednesday. Let's see what we cover after the 25th. And then I'll let you know what's the material. But it seems that's going to be chapter 1 and 2. Okay, plus lab 1. That's what it looks like. Plus the material of lab 1. Material for chapters 1 and 2 and lab 1. And let's take a look here at the notes. Here you go. Exam is on Wednesday next week, October 2nd. October 2nd. Yep, October 2nd. 9 days from now. So far, the material will be the following. So far, the material will be the following, right? Chapters 1 and 2, I'm hoping to cover it today. Finishing covering today. Today and finish covering today. Plan to finish covering those two things that are left. And let us come up with a summary of vectors so far. Am I sharing the screen? Yes, I'm sharing the screen. Good. So vectorial representation, there is the graphical representation, right? And two, the mathematical representation. Letter with an arrow at the top. Now, what I didn't mention to you that there are only certain operations that are allowed with vectors. Only certain operations. So far, we saw the following operations. Multiplication, scalar multiplication with vectors. You can do that. Scalar division with the vector, with a vector. You can do that. Vectorial summation. You can do that. And vectorial subtraction. The vectorial subtraction is just a special case of the vectorial summation, right? Just a special case of the vectorial summation. Because you're summing a negative with another vector. You're summing the negative of a vector with another one. Remember that. And then there are operations that are not allowed in this course, at least for the sake of this course, okay? At least for the sake of this course. Later on, if you go to advanced math, you're going to see that there are some operations that are allowed. Some of those operations that I listed here may be allowed, okay? But for the sake of this course, you cannot multiply one vector by another one. But I mean the regular multiplication, right? The regular multiplication between vectors is not allowed. You cannot divide one vector by another. You cannot divide a scalar by a vector. But you can divide a vector by a scalar. You can do the opposite, right? You can do this one, but you cannot do this one right here. You cannot commute. What else? Graphical summation, subtraction between vectors. Right? Two techniques. head to tail, and the parallelogram method. The magnitude of the summation and subtraction between vectors, right? Now let's take this one out. The magnitude of the summation between two vectors can be obtained using the cosine law. That's what we saw so far. And let me put that between quotes, because it's not a law. It's actually is a consequence of something else. And what we're going to do now, we're going to do vectorial components. This is the new material and the last material in this topic of vectors. The nice thing about vectors is that it can be expressed in terms of components that lie along the x and y axis, okay? I'm going to show you. That's how we represent those components. You know, a given vector can be rewritten in terms of components along the x-axis and along the y-axis. It's possible to do that. And I'm going to illustrate that for you here. Here you go. Here's the vector A, okay? And here the x component of the vector A and the y component of the vector B. See, it's the projection along the x and y axis. And when we do that, it becomes very convenient to add vectors. Here you go. All those two components displayed simultaneously. Okay, and that's what I did there. See, AX vector, the component of the vector along the x direction, plus the component direction of the vector along the y direction. This sum here is equal to the original vector. What else can we do? Let's copy that. Let's copy that into our notes. But then you can go further. You can go further than that. Okay? And instead of writing the x component of A as a vector, instead we choose to first define, let's see here. Okay, define a unit vector along the x-axis. Okay, and I call it, every unit vector is going to be denoted by this hat here at the top. And why unit vector? We'd say unit vector so this guy here doesn't change the length of the component of the vector. The magnitude of this unit vector is 1. Okay, so we don't change the magnitude of the component of the vector. And we can also define, and it's a very convenient definition, another unit vector that we call y hat, okay, along the y direction. Most books call it j hat and I hat. I hat, j hat. Okay, I prefer to tell my students, look, I prefer to tell my students that those, I prefer to use this notation here, x hat and y hat. Okay, it's not wrong to use y hat, I hat. It's not wrong to use j hat. My preference is to write them down as x hat and y hat. And when we do something like that, okay, Now we can write each separate component, each separate of component AX and AX vector and AY vector as a scalar that I call AX scalar multiplied by X hat. The component, the scalar component, right, of the vector, and AY times Y hat. Okay? You're going to see why it's very convenient to do that very soon. It's very convenient to do that when you sum, okay, vectors, when you subtract vectors. If we analyze this figure, we can see that AX, the X component of the vector, is going to be its magnitude of A times cosine of theta, right? Given there in the figure. And let's not forget the X hat unit vector. And let me write that down. I'm gonna put it right here. Where? Huh? Where X hat equal to Y hat, but I gotta put the magnitude there. Let's put the magnitude first. X, magnitude of X hat is equal to magnitude of Y hat. Which is equal to 1. Okay, and we can do the same for a different vector B. There's a reason why I am doing that. And that, let's see if I can illustrate the B vector here. That's the B vector here. I put theta here, right? I should put theta prime here. Oh. Okay, I cannot find a prime here. Well, let's leave this way. Let's leave this way. Okay. And here you go. That's what I did here. I just repeated what I did right here, right? Vectorial component of X, vectorial component of Y. And then the vectorial component can be written as the scalar Bx times X hat and the scalar By times Y hat. This is a summation of two vectors, right? And, can be here written as B, magnitude of B cosine of theta prime, right, in the X direction. Magnitude of B sine of theta prime times Y hat. And what I meant is, see, the A I meant, yeah, okay, let's copy this one. Like that. Okay. And then I'm gonna go with an example. See, I'm giving a numeric example. Bx is 3x hat, right? But now, if we use now this new definition in terms of components, now it becomes much easier to sum up the vectors mathematically. Okay, so here you go. A vector plus B vector, right? I here write that in terms of the components. Look, now these two, they don't sum automatically because they're perpendicular to each other. They have different directions. Not just they are perpendicular, but they have different directions, right? But if I combine the components that have the same direction, then it becomes easier to operate on them mathematically. Becomes easier to operate on them mathematically. And that's what I did here. See that? I combined this with this one, and it became that. Just the summation of three scalars. And I combined the red one with this one, and I got something like that. Okay? Likewise, we can define the summation as being a third vector C, right? And if you have a third vector C, this third vector C can be here written in terms of its components as well. Okay, there you go. I'm gonna put it, write that down like, oh, nope. Copy. And here I'm going to write it as A plus B as well. Just repeat what I have upstairs. Okay, and now we can come up with the examples, numerical examples. Okay, so let's say, let A be 5x hat plus 7y hat, and B equal to that. Find the vector A plus B. Straightforward, right? Find the vector A plus B. And here's the solution. You just go ahead, write down A, write down B, and well, I'm gonna come up with another step here that I didn't do. Okay, I will commute, right? This with this, and this with this, right? I can go ahead and do one more step. And the other step will be this one. Right? One more step. And this other step would be like that. And now we can come up with the final answer. Oh my goodness, here you go. Now we got it. I'm not going to boldface it. Let me take out the boldface. And we're going to do another example. What? I'm gonna ask you, what is, for some reason my keyboard is not doing everything it's supposed to do, right? Find another example here. Find the magnitude of the above resulting vector, right? So I know that the vector can be written down like that. And now we want to find oh, too many. Hey, my computer is so sluggish. What's going on here? Maybe I have to make, my goodness, look at that. Okay, now I'm gonna put the magnitude of this guy here. Right? I'm gonna put the magnitude of this guy here. Right? And let's see if I have here an example, right? I have here an example. Let's see if it's the same example that I'm doing in the book. No, it's not the same. Okay, but anyway, if you do this summation, right, the resulting vector is going to have an x component and a y component, right? Is a right angle triangle. Consequently, the final vector must have a magnitude that's going to be given by the square root of 6 square plus 17 square, right? And then you can do this math. 36, 17 square is going to be what? Let's get the calculator here. 17 times 17, 289. And then we want 289 plus 36, 325. 325. And then we have to take the square root of this value. I'm getting 18.02. Okay, 18, let's see, 18.02 should be, yeah, very close, 18.02. And that's what I did here. Okay, we don't need that, just a repetition. And then you have others too. Oh, I'm asking the angle now. Let's look at the 5x, 7y. Let's see. No, I don't have 5x, 7y here, unfortunately. Yeah. But if you want to know the angle, right, that the vector, find the angle makes with the x-axis, just look at the resulting vector right here. The resulting vector c makes this angle right here, right? The angle that it's going to make is the tangent of this angle here is going to be the magnitude along the y-axis divided by the magnitude along the x-axis. You can see that easily just by making those drawings. Okay, and then we found out the IA plus B vector. So it should be I'm going to put it here. Ah, like that. Okay. I'm going to come up with another step here. Oops. Just like I said, my computer is behaving oddly today. Okay, X component, not X component, Y component, right? And I'm gonna write down like that. Y component plus Y component of B, and I have to put it in terms of magnitude, right? X component. Oops. Just replace it. And then you take the arctangent of this value here to find the angle. Okay, and that. Oh, and we still have vectors in 3D space. Okay, we still have the vectors in 3D space. I have to tell you that before we finish the chapter. You know, it's all you have to do is to add the third component to the vector, right? Add the third component to the vector. The magnitude of each vector is going to be given, because all those three components are perpendicular. It's still going to be given by this summation of the square of the three components, and then you take the square root. Okay? If you want to find out the angle theta that the vector A makes with the z-axis, I'm going to show you. Let's see if I have one three-dimensional example here for you to see. I have it right in here. Showed to you last time. Remember that? Oh, right in here. Okay, here you go. Here's the vector. Here is the x component of A. Here is the x component of the y component of A, and here's the z component of A. I'm going to draw that for you, just like I drew before. Oh, x component of A y component of A and then we have the z component of A. See that? How it's summed, how those vectors sum up? I will use those right here. AX, AY, component X, component Y, component Z, component Z. like that. Try to practice doing those drawings, 3D drawings. Okay. And then what else do we have? If I want to know the angle theta that the vector makes with the z-axis, just refer to your drawing, right? Just refer to this drawing right here. I will draw this one that I want. And I need some more stuff here. Okay, now I'm not going to struggle with that. Let's see, maybe I will. Draw, design, transition, animation, slideshow. See, view. That's what I want to view. Grid lines. Okay, I found what I want. Right in here. Here you go. That's the angle theta. I want a secret. Yeah, that's what I want. Theta. Good. That's the angle theta. And this angle theta is going to be given by what, right? This angle theta here is going to be given by this component, which, by the way, I'm going to call you. I can call you. This one is another component that I didn't label for you, okay? Jesus. Ay, 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 ay. Huh. Yeah, my computer is really strange. It's not copying everything here it's supposed to copy. Looks like my problem is in my keyboard. Let's see, paste. Okay, finally. XY. Okay. And I even going to display it. See that? Oh gosh, that's terrible. Why is it behaving like that? I'm gonna do copy, paste. Yeah, I'm gonna do the okay. It's another way, right? Can even put this way. See, AX plus AY is equal to this one, right? And if I want to know this angle right in here, look at the triangle that I have here. If this one is AXY, this also is going to be AXY. Huh. Okay. And look at the triangle, right angle triangle that we have here, right? So I'm going to emphasize that it's a right angle by placing a little square here. Not exactly this one. I'm going to put another one. This one. Yeah, let's see. Like that. Like that. Like that. See that? Outline is going to be black. And then we finally put a that's not a very good square here, but hopefully you believe me. And then I'm going to put a little dot there. Okay. Make it look nicer. Right angle triangle. So what's going to be the tangent of theta? Tangent of theta is going to be this one that you see here. I'm even going to put the magnitude too, okay? Magnitude and magnitude. Okay. Type of problem you have to make the drawings, okay? You have to make the drawings to visualize the solution of your problem. Now, if you want to find out the angle alpha that the vector of that the vector along the xy plane, okay, makes with the x-axis, right? Oh, if you want to know the angle, this angle right in here, all you have to do is ay over ax, right? Ay over ax, but let's not forget is the magnitude. Okay, so we did everything. And we have more examples here. You can look there at home. Let's make sure they're not exactly the same, right? Like 5x, 7y. Ah, yeah, they're the same. So you can erase it here. And yeah, you can erase it. We have 18 students so far, 9:30. Just to remind you, for those who arrived a little bit late and missed, right? We have an exam on Wednesday next week. Chapters 1 and 2, and lab plus lab 1. I'll try to make it an exam that, rather straightforward, okay? But keep in mind, there are questions that are very straightforward, right, to solve. And then there are questions that are more difficult, both mathematically and from the interpretation point of view. Could go back to the operations you cannot do with vector. Oh yeah, I can do that. Let's see, 289, Danae. Was that 289? Are you referring to the 17 square? Yeah, here you go. I put 17 square here. Thank you, Danae. And I respect to know, oh yes, you respect to the 3D. Yeah, practice that. It's not difficult, okay? It's not difficult. And
Then
I'm even going to do the step by step, right? First, you draw, let's see. Let's do the step by step here. The challenge first is to draw the X and Y axis, right? That's the first challenge. Okay, I'm going to erase here the presentation of a 3D vector. Start with the X axis, right? Then you go ahead, draw the Y axis like that. Don't forget to label it.
so how do we know, like for the x-axis, is there a certain angle we supposed to be drawing it at, or we just draw a
Well,
diagonal line?
yeah, you mean how do you know in which direction is the X, Y, and Z? That's what you're mentioning. That's what you're asking.
Like instead of it being like the normal x, y, like the x being horizontal and the y being vertical, is
Yeah,
uh
yeah. If you do this way, you won't be able to have you won't be able to have that illusion, right? That the you're talking about doing that like that, right? X here, right?
yes.
And then if you do this way, you won't be able to have that illusion that the axis is a three-dimensional one. Okay.
So it doesn't have to be like a specific angle in which we do that. We can just draw a random diagonal line to make it the 3D presentation.
Yeah, let's see if I can do is this one. Let's see if I can do is this one. Maybe we can do is this one too. Let's see. This one's gonna be y-axis, right? We usually do that way that I was doing, but there are other ways of drawing too. Okay, you can let's see if we can get the illusion, right? That there is a three-dimensional. There's a three-dimensional. Yeah, see that? That's another way. That's another way. Okay, do you get it? Yeah, can you picture that? Works, right? We have the
Yeah.
illusion that we have the illusion. It doesn't matter if you draw this way or the other way. Okay. But the important thing is that you have to use the right hand rule. Okay. You have to use. And what do I mean by using the right hand rule? Okay, for drawing those axes. Otherwise, you're not going to get the proper direction. Okay. When you lay the palm of your hand along the x-axis, but it has to be the right hand, not the left. Okay, and then you curl it, towards the y-axis. The thumb must point in the z direction. Okay, and the same thing for x, y, z too, right? There you go. Y, z. The thumb must point along the x-axis, and the zx must point along the y-axis. Okay, it should be incorrect. It should be incorrect if you draw the z-axis in this direction. Okay, because that would not obey the right hand rule. Okay, so but it's an important detail that you gotta know, so you can draw those axes in a proper way. So that's one way. Okay, let me give you another example. The other example is that one that you saw before, right? X. Oh, here you go. X, Y, and Z. Okay, that's another one. They're still exactly the same axis. They're exactly the same axis. You are just looking them at a different angle. Okay, but they are exactly the same axis. And then there is another one. You can play around with that. Let's see what we have now. We have X, Z. Already did this one, right? I put the Z here. Let's see. Yeah, I put the Z here. Z, X, and Y. I'm gonna rotate them cyclically. Okay, here you go. The other one should be Y, Z, and X. Three different ways of representing the three-dimensional space. They are all the same and correct, okay? Let's see, this one is the one that, okay? So I'm giving options to, you go, now we got it. X, Y, and Z. This one is the representation that we see the most out there. This one here is the representation that we see the most out there, okay? But you can also do this way. But make sure you, when you place the X, Y, Z axis, make sure that they obey the right hand rule, okay? Make sure they obey the right hand rule. Let's say when I, and by, let's say, correct representations, right? Now I'm going to show an incorrect representation, okay? Incorrect representations of the 3D space instead of 3D vector, right? We call it the 3D space. That would be the most challenging thing, incorrect representation of the 3D space. If you do something like that, that would be an incorrect representation of the 3D space. Okay, and I'm going to emphasize, emphasize with red. Okay, another incorrect representation. Again, if you point the y-axis downwards, another student coming in, we go. Incorrect. And finally, the other incorrect representation is this one right in here. Okay. So practice that a little bit. Okay, X, Y, and Z, right? Here's the vector. AX, AY, AZ components. You know, and you also have the AXY component, the component of the vector projected in the XY plane. That's the XY plane.
And these are all expected to be right triangles from
What,
this.
what, what's the question?
And these are supposed to be right triangles.
Right triangle, yes. Yeah, there's a right triangle here, right? You're asking a right triangle, right?
Yes.
Yeah, there's a right triangle here. There's another right triangle here. There's another right triangle here. There's another right triangle here. All those axes, they must have 90 degrees. They should be, you know, they should make an angle of 90 degrees. All those
Oh,
axes. X,
okay.
Y must make a 90 degrees with each other. Z, Y must make 90 degrees with each other. And, right? And the XZ must make a 90 degrees with each other. Let's see. Let's do that with the 3D space, right? That I drew before. Once you get the hang for it, it's it becomes really fun to draw those things. Okay, here you go. And I'm gonna fill with nothing, right? I'm gonna make a thicker, yeah, thicker, and should be black. I prefer black, right? And now I'm gonna draw another one. And maybe we should do, instead of black, maybe we should do different one. Okay. Yeah, let's do red, right? So it doesn't disappear there in there. Another one. Let's see if I draw it properly. One. See, where I'm drawing it parallel to the y-axis, right? First I draw parallel to the y-axis, and then no, I don't like that. Yeah, kind of ugly, isn't it? Let's see. Yeah, it's a little bit ugly. Let's try it again. Yeah, it looks like it's better now. Hope so. Okay. And let's make it no fill. Okay, and then I'm gonna make it a different color instead of red. I'm gonna make it green. Make it a little bit thicker, right? And now the last one. See the 90-degree angle that X makes with Y, 90-degree angle that Y makes with Z, and then we have one more to go. If you do that by hand, it goes much quicker, okay? The 90-degree angle that the X-axis makes with the Z-axis. Let's see, red, green, and blue. Yeah, let's put blue here. Blue and no fill. I'm gonna make it thicker. And a little bit, I don't like this, but that's okay. Okay. Would be better, right? A little bit twisted. Let's see if I can do better. Nope. This one here. Well, this is not the way I like either. Let's keep the other one. It's not ideal, but it's better than the second one that I drew. Okay? But that's how you should be doing those axes, okay? 90 degrees. What time is that? 9:45. Okay. And then, you know, you draw the vector, right? Get the arrow. We go. Right in here. And then you project over the XY plane, project along the Z axis, right? And project the vector along the XY plane in the Y direction and in the X direction. Okay. Any questions? Let me see. There's more. Would you provide a study guide? Yeah. Yeah, we'll provide a study guide. And let's take attendance now. Any more questions? 9:31. Let's get the roster. So, 18, right? Yeah, this one goes right in here. That's the 23rd. Audrey Aguilar, are you there, Audrey? I can see Audrey here in my roster. but I don't hear from Audrey, so I'm gonna put a star for now. Matthew Aguirre.
Good morning, Professor.
Morning, thank you. Darius.
Good morning.
Good morning, Darius. Brianna Carrillo. Good morning, Brianna. Hi, Andre. Okay. Okay, thank you, Brianna. Okay, Audrey is here. Next, Jazzy. Hello, Jazzy. Good morning. Doesn't look like Jazzy is here. Castellano. Yeah, Jazzy is not here. Gabriel Contreras.
Good morning, Professor.
Good morning, Gabriel. Next is Liliana Cortez. I don't see Liliana here. Juan Salvador Escalera. Thank you, Juan. Molly. Molly is definitely here, right?
Yep.
Okay. Henry Kim. I don't see Henry here. Yeah, next. Ruth Mandujano. I don't see Ruth either. Next is Noemi Martinez. I don't see Noemi either. Let's see, Danae. Danae is here, right, Danae?
Yes, sir.
Okay, Ramon Olivares.
Here, Professor.
Thank you, Ramon. Taylor Forn. Taylor, I don't see Taylor here. Next is Alexis Quijada. Nope, no, don't see Alexis. Stephanie Ramos.
I'm right here, Professor.
Okay, thank you, Stephanie. Next is Jeremiah Reyes. Okay, good morning, Jeremiah. Thank you. Sean Rosario. Okay.
Here.
Okay, Sean is here. Ali Standard.
I'm here.
Thank you, Ali. Next is Jason Strait.
Here.
Thank you. Elena Trujillo
Here.
joining us. Okay, Elena just answered, right? Yeah, okay, Elena T, good. Jason Paladares.
Here.
Thank you, Jason. Stephen Vathapali. Stephen, okay, thank you, Stephen. Next is Laurel Williams. Okay, thank you, Laurel. Next is Nuhamin Wandimu. Thank you. Alia Zavala. Let's see, what about Jazzy? Hey, Jazzy, just joined us, right? Can you hear me, Jazzy? Okay, I'm gonna put the star in Jazzy's name. Oh yeah, here you go. Now she answered. Thank you, and let's make sure everything is summing up. Yeah, 21 here. Good, 21 students in the list. 9:51, and let's go to our break for our break. And when we return, we continue, we start chapter 3, okay? Break after the break, we will start chapter 3. And let's take a look here, the book. Okay, that's we finished chapter 1. Units, role of units in problem solving, trigonometry. I didn't cover trigonometry because it's already requirement for the prerequisite for this course, right? Scalars, vector we covered, the vector addition, subtraction we covered, the component of vectors, x and y component, x, y, z component, addition of vectors by means of components. We cover all of that. Displacement 1D. Displacement, speed, velocity, acceleration, equation of kinematics, right? Constant velocity, constant acceleration, okay, and so on. And then we did 1D, kinematics in one motion, right? And now we're going to do kinematics in 2 and 3D, in 2 dimensions and 3D dimensions, right? Displacement, velocity, and acceleration in the 2-dimensional space, and can be extended easily for the 3-dimensional space. Equation of kinematics in 2 dimensions and also in 3 dimensions. And then we have this important application of 2D motion, that's projectile motion and relative velocity. That's what we are going to do next. After the break, we start chapter 3. Break from 9:54 a.m. to, let's see, 10:09. Yeah, until 10:09 a.m. Okay, so see you in 15 minutes. Stop sharing. Now, I want to remind you of the scalar quantities that we have discussed before. Some of those scalar quantities is positive, are positive only, right? And length is a positive quantity, but it's not the same as position. Time is a positive quantity. Mass is a positive quantity. Distance traveled, speed, they are positive quantities. And then we have vectorial quantities as well. Okay, I already told you that position and force, we didn't cover force yet, but position, force are vectors, are vectorial quantities. Let me put the force right here. Force is a push or a pull. And we usually represent the position vector with the letter R. Okay? How do you get things? Okay, better. Here you go, position with the vector R. Then by the same token that we have displacement in 1 dimension, okay, here you go. By the same token, we have displacement delta x in 1 dimension, comma, we will also, not may. We also have displacement in 2 and 3 dimensions. Okay, if in 1 dimension we represent the displacement by delta x, in 2 and 3 dimensions, we represent the displacement by delta r, represented by right? Delta R. And delta R is going to be, here you go. I'm gonna put delta X and delta R just next to each other. Okay, here you go. The delta R is going to be R vec, but it's gonna be final vector position, right? And make sure that you understand it's a final vector position minus initial vector position, and the initial vector position is the R naught. But to simplify the notation, we just drop the final subscript, but just for simplification, for simplification's sake. Okay, here you go. Rf is equal to R. And in the one-dimensional case is, delta X is xf minus xf minus x naught. And for sake of simplicity, we drop the f subscript, okay, like that. One-dimensional case, two- and three-dimensional case. And I'm going to put displacement here, because displacement depends on the position, right? Well, just following the same script that we have for one-dimensional. For the one-dimensional case, we also have the average velocity. And we represent the average velocity with the vector notation, with the arrow there at the top. Okay. The vector average velocity is defined just in the same way as the 1D velocity, average velocity. So like that, you go, average. Oops. Average. Make it nice, I want it. Yeah, here you go. Delta X over delta T, okay? I don't need the rest. And all I have to do here is to put the vector symbol, the arrow symbol there at the top, and replace the delta X by the delta R. Do you see here? A vector is being divided by a scalar. That's allowed. That's an allowed property. And the instantaneous velocity vector, right? and the instantaneous velocity vector. The instantaneous velocity vector is velocity vector is defined the same way as the 1D velocity, right? We have that limit situation, and then we have let's see, let's hunt that down there before. The definition that we did before. Yeah, that's the one I want. Here you go. And then the velocity vector is exactly the same thing. And we put a delta R over delta T here inside. When delta T goes to 0, delta R goes to 0 as well. Not a finite number, but a finite vector. Okay? And finally, we have the acceleration, right? Average acceleration. First is the average acceleration. Oh. Okay. Average acceleration, and then the instantaneous acceleration. Instantaneous acceleration. Go average acceleration. Like that. And then the instantaneous acceleration. Like that. Finite vector. And you can go ahead and write down all those quantities, right? As their x and y components. And they are writing here, for instance, the initial position, right? All those quantities, all these quantities can be written in terms of their x and y components. Okay, here you go. Initial position initial position along the x-axis, initial position along the y-axis, final position, right? And then if you want to write down the delta R, let me take this one out, we don't need that. We just go ahead and write that in terms of the components of delta R. Okay, here's the initial position, here's the final position. We collect all the components along the x-axis to simplify our notation. Why it's not? Let's see. Yeah, just like I did here. Yeah. Yeah, he doesn't like it. Okay. Here you go. In the next step, right? Here you go. Collecting the x components and the y components. And look what we get. We get delta x along the x-axis, delta y along the y-axis. Okay? Average velocity, same situation. Okay? Delta x along the x-axis, delta y along the y-axis. And look what we get. The average velocity, can be broken down into x and y components, right? Delta x over delta t is the velocity along the x direction. Delta y over delta t is the average velocity along the y direction. And here you go. And the same can be said about the other quantities as well. Here you go, limit the instantaneous velocity. The same can be said about the instantaneous velocity. It's going to have an x component. It's going to have a y component. The same can be said about the average acceleration and the instantaneous acceleration. Okay. Let's take a look at the illustrations as well. So I'm going to illustrate all those quantities here. Not this one. 2D motion genetic. Yeah. That's the one I want. Okay. 2D 2D motion graph. Because now we have 2D motion, two-dimensional motion, we have to depict the two-dimensional motion, the x and y plane, not just along the x plane, right? Or the y, or not just along the x direction or along the y direction, but simultaneously along them. Here is the XYZ plane, XYZ space. Okay, that's a type of 3D, right? Kind of a 3D. Here you go. And let's go back to the 2D. Then we worry about the 3D later on. X direction, x-axis, y-axis. And if you want to depict a XY, a two-dimensional motion, we can depict the path of the particle like this curve that you see right here. Okay? At a given instant of time, the particle is here, and its initial vector position can be denoted by this vector from the origin towards where the particle is. Okay? Delta t equal to 0. And the coordinates of this point are x0 and y0. Initial position along the x-axis, initial position along the y-axis. Okay, here you go, and my vector being here written in terms of its components. the final position of the vector at t equal to tf greater than 0 is going to be this vector that you see right here. Different from the previous one. That's a very generic situation that I'm drawing here for you, okay? Later on, when I show some specific examples. And now we have the initial position and final position. And by the way, RF minus R naught. What is RF minus R naught? Okay, is going to be this vector delta R, right? Do you agree with that? Okay, this one, what you see there is the R naught, but then I'm going to draw the minus R naught. The minus R naught will be drawn like the following. Okay? And I'm going to specifically state here minus R naught here. Right? RF plus minus R naught goes from the tail of one vector to the head of the other. Okay? Here's a summation, right? Between RF and minus R naught. Very important that you get this idea, right? You go, here's the method of the parallelogram. Oh, it's not the method of the parallelogram. It's, I'm just projecting the same vector delta R right here. That's all. That's all I'm doing. Okay? And let's not forget that because the average velocity is defined as delta R divided by a scalar, the average velocity vector will be parallel to delta R. It's just the magnitude is going to be different. The magnitude may be different, right? And on the top of that, not just the magnitude is different, but it also has different units. The average velocity vector still have units of meters per second. The delta R vector still have units of meters. Still have units of displacement, right? And what do we have now? Okay, here you go. This is the delta R vector being broken down into two components, the X component and the Y component. The average velocity vector 2. Okay. And depending on the scale that we use, the average velocity vector is going to be displayed differently, okay? So let's see, okay, so let me just go back to my notes. By the way, this thing doesn't fall in the exam, okay? It's just chapters 1 and 2. Okay. I'm going to write that down right here. Here you go. The average velocity vector is parallel to the displacement vector. Okay? The average velocity vector is parallel to the displacement vector. Okay, here, the direction of the instantaneous velocity vector will coincide, right, with the direction of the displacement vector as it tends to 0, right? As it tends to 0. Similarly, here you go. The direction of the average acceleration vector, instead of the direction, right? The acceleration, the average acceleration vector has the same direction as the delta v vector, right? Because we have a scalar here. Scalar doesn't have any direction, right? As the delta v vector, which, by the way, is v final v final minus v initial. And let's try to visualize how does it look like, right? So if I want to find out, for instance, the instantaneous velocity vector, the direction of instantaneous velocity vector right here at this point, right? What do? We do that same thing that we did before. Let's see. No, I want to find out the instantaneous velocity vector right here at this point. Velocity vector at the middle point. Let's see, at the middle point, right? What we have to do? We have to get the points that surrounds it and make their difference going to zero. Here you go. You see what's happening? The delta r vector is shrinking, but it's tending towards a direction that's tangent to the path. Okay? As delta r goes to zero, it becomes delta L. Okay, delta L. Tangent to the path, Like it here, okay. Tangent to the path. Your path. Let's see what's going on here. Okay, so here you go. The velocity vector is tangent here. The velocity vector at this point is going to be tangent here, as well as the delta r, right? As it goes to zero. And tangent here, right? Here is V1, here is V2, here is V. Can you remember that? Okay, here you go. So, going back here. As delta t goes to zero, comma, the instantaneous velocity vector tends to be tangent to the path of the particle at a given point. Okay? That's what you have to remember. If delta t goes to zero, the instantaneous velocity vector tends to become tangent to the path of the particle at a given point along the path. Okay, that's what you have to remember. Okay, so here you go. Here's 1D motion along the axis, right? And here 1D motion restricted only to the y-axis. Now we are doing both, right? We're doing both motions. Okay. Now that that you have an idea of two-dimensional motion, so don't forget, the two-dimensional motion is a combination of those two vectors, right? That's what it is. It's a combination of the vector along the x-axis and the vector along the y-axis, the summation of those two vectors. That's what you have to keep in mind. Now, okay. Now suppose that you are given this path and those vectors. You should know those vectors, okay? You should be given those vectors should be given to you for you to solve the problem. Now tell me what would be the average acceleration vector between the following points. Okay, the average. Try to do that yourself. You know, make a drawing there in your notebook, and then I'll walk you through. You know what you want. What you want to do is first find the average acceleration vector, the genetic direction of the average acceleration vector between points 1 and 2. Okay, then between points 2 and 3, and then between points 1 and 3. Right? I'm going to help you out. Let's do between points 1 and 2. Right? Find the qualitative direction of the average acceleration vector between points first, right? Points 1 and 2. 1 and 2. I'm going to erase this one here. You don't need that. Right? First, this one. In order for you to do that, this is a genetic example, right? Find the genetic direction of the average acceleration vector between points 1 and 2. 1 and 2, okay? So even better, given, all right? The path of the particle, comma, the direction and magnitude of two instantaneous velocity given. Then I'll list that for you. You know? So you know what's being given. Given 1, the path of the particle. 1, the direction and magnitudes of two instantaneous velocity vectors. And 2, the directions and magnitudes of two instantaneous velocity vectors. Find the genetic direction of the average acceleration vector between points 1 and 2. And then I'm going to copy that. So you have something in your notes, right? You have enough time to do that? Like that. Yep. Well, the first step is to go to the definition. Go back. Go back to the definition of average acceleration vector. Go back here. I'm going to copy it. Here you go. Right in here. Right? Delta V over delta T, which, by the way, it's final velocity minus initial velocity. Okay? In this case, the final velocity is going to be the V2 vector. And the initial velocity is going to be the v1 vector. Do you agree with that? Okay. So we have to do this, this vectorial operation. Okay, we have to do this vectorial operation. We have to sum the minus v1 vector with the v2 vector. And we can do that right here in my PowerPoint. I will make sure that I will display only the two vectors that we are interested. Everything else we can get rid, right? Here you go. Here are the two vectors. I'll keep, I don't need the paths. I'll keep the x and y axis. Okay? And then I'm gonna put, initially I'm gonna put them tail to tail. This is still the v2 vector, right? And then what I'm gonna do, final velocity minus initial velocity, right? I have to invert the direction of this vector. Okay, and don't forget that I to put the minus sign here. Okay, so here you go. Get the initial vectors, put them tail to tail, and then invert the direction of the initial vector velocity. And then you have to draw the resulting vector, the resulting summation of those two vectors. Like it here, I'm going to, that's okay? Yeah, let's put this one like that. And I am going to and draw it as a nice blue. That's the resulting direction of the delta V, which by the way is parallel, okay, to this delta V. I'm even gonna put it here. Right? Oh. Like that. Which, by the way, is parallel nope, not what I want. Which, by the way, is parallel to the average acceleration vector. Let's see if I can get parallel here. No, not this one. Yeah. I'm gonna put it side by side here, like that. And I'm just gonna increase right a little bit. Maybe it's gonna have a, and that would be my, yeah. Acceleration vector, average. I'm gonna AVG. Parallel to delta V. Or we're gonna put over there. And I'm gonna put a different color so you know it is a different quantity. Okay. Now, getting this thing back to our drawing there, the path, right? Drawing of the path. I'm going to copy this one here. Look what you end up getting. Don't forget this delta V is somewhere in between those 2 points, point 1 and 2, okay? Note what you should note. You should note that this vector is pointing towards the center of this concavity. This is no coincidence. Okay, this is no coincidence whatsoever. I'm gonna copy it here and place right here. This is no coincidence whatsoever. We actually find that the average acceleration vector is always pointing towards the concavity. Okay, the concavity of the path. And I'm going to also to draw my, here you go, my average acceleration vector right here. Let's place them a little bit displaced side by side. Like that, okay? Let's go to our notes. Here we go. And I'm going to copy. Okay, this one that you see right in here. And put it in the notes. The next one. 3D of a 3D space. It should be 3D space here. Of the 3D space. See here. We gotta close this one. We don't need that. Okay, and we need this one. Yeah. One more. Here you go. Notice that both the delta V and the average acceleration vectors. Notice that delta V and the average acceleration vectors, comma, they both point towards the center of the concavity of the path. Concavity of the path. This is no coincidence. This is no coincidence. No coincidence as these two vectors will, these two vectors and their instantaneous counterpart will always point towards the center of the concavity of the path. Okay, can you remember that? Very important result here to have in mind. Okay, and then you can do for the rest. You can do for V2, V3, okay? V2 and V3, you can do about V1 and V3. In the case of V2 and V3, right? Let's do for V2 and V3. You go. I will take away the pass. I don't need this guy. I don't need this guy. V3 minus V2. The next, just another example. Here go. V2 is going to be here. First we put them tail to tail, right? And then we invert its direction. Yeah. And then I can denote like that. Okay, between V2 and V3, you can see the concavity is still downwards, right? The concavity is still downwards. So let's continue with our put that in color. V3 minus V2. And then we put that here. And then we can put it back there in our drawing. V2 and V2. I don't need this one right in here. V3 minus V2. There you go. Somewhere around here, in between those two vectors, right? Still point towards the center of the concavity. Okay? And then you can repeat for another one. Let's say V3, V2 and V4. Okay? Let's say there is another vector right in here. V4 right in here. Let's take V4 and V3. You can repeat for V4 and V3. So practice that at home, right? Practice that at home. One more student coming. We're getting to the point that we need our break. See. Okay. So take another break. 11 a.m. to 11:50 a.m. Any questions? Do you have any questions? Okay. So let's take our break here and I'll talk to you soon. Stop sharing. Okay. Let me give you another example here. That's in my notes, in my PowerPoint, right? So here you go. Okay, so here you go. Here's a different path than the one that you saw, okay? The average acceleration vector between V1 and V2 will be somewhere in this direction. Okay, towards the center of the concavity. Because this vector velocity is much longer than this one, then you should expect, the average velocity. Let's see. Let's do that, right? Here you go. V2 minus V1, right? V2 minus V1, look what happens. It's going to be really in this direction that I mentioned, right? Now, we're talking about the average acceleration vector, right? But don't forget, the average acceleration vector will point towards the center of the concavity only if you're taking 2 points, in the edges of the concavity, okay? It's very important to point that out. If I go ahead and take the average acceleration between V1 and another velocity vector like this one that includes 2 concavities, now I won't know whether the acceleration vector is going to point towards, towards this concavity or this concavity, okay? However, the instantaneous acceleration vector will always point towards the concavity. That's what you see here. The instantaneous acceleration vector in this case will always point towards the concavity. Here we have another concavity right in here. So my instantaneous acceleration vector will point towards the concavity as well. Okay? Can you memorize that easily? That's not difficult, right? Here you go. Acceleration vector 1, acceleration vector 2, acceleration vector 3, right? And those acceleration vectors can be broken down into 2 components as well. One that's tangent to the path and another one that's normal to the path. And normal to the path means perpendicular to the tangent. So that's the genetic treatment of the 2D motion, okay? So let's summarize here. Summary of the genetic treatment of 2D motion. Motion. One, must have the path drawn 2D/3D. Let's put here. It's also all those concepts apply to the 3D motion as well. Must have the path drawn in the 2D/3D space. Okay. Two, what you have to say, okay? The instantaneous velocity vector will always be tangent to the path, okay? The average acceleration vector will point towards the concavity of the path if the 2 points are at the edge of the path of a section of the path, right? At the edge of a section of the path with a single concavity. Okay? Well, okay, so here you go. So here you go. Let's do it this way. Here you go. Point towards the concavity of the path if the 2 points are at the edge of a section of the path with a single concavity. Concavity, yeah. Here you go. B. If the 2 points encompass more than one concavity, if the 2 points encompass 2 or more different concavities, nothing can be said about the genetic direction of the acceleration of the average acceleration vector. Okay. Now, for the instantaneous acceleration vector will always point towards the concavity of the path. Okay? So those are the 4 important points that you must have in mind, okay? So here you go. Let me just illustrate it here again, right? So suppose, okay, so here we have a concavity, here we have another concavity, and here we have another concavity, 3 concavities, right? If I take the average acceleration vector between this point and this point that at the edge of a single concavity, I know for a fact that the acceleration vector, is going to point towards the center of the concavity. I just do not know exactly the direction, but I can make this statement that the the average acceleration vector will be pointing, towards the center of the concavity. However, if I have a region here, if I'm taking the average acceleration between a point here and another point right in here, right, that encompass two different concavities along the path, then I cannot say where the average velocity acceleration vector is going to point. Okay, that's what I meant. However, if I come to you and say, look, which is the direction of the instantaneous acceleration vectors at different points? Okay, at this point, I know for a fact that it's going to point towards the center of the concavity. At this point, I also know that it's going to point towards the center of the concavity. At this point, here you go. We have a different concavity here. Consequently, the acceleration vector, the instantaneous acceleration vector, is going to point towards the center as well, and so on, including this A3 here. See the concavity here? The concavity, the curvature, right? This A3 is the good indication of the direction of the instantaneous acceleration vector. That's what I meant right now, right in here. Okay. Any questions? Don't forget that this part here, chapter 3, will not show up in the exam. Okay. And now that we studied the genetic case of a 2D motion, let us look at a more specific case. Okay, we are right in here. 3.1. Come on, man. It's taking time. Let's see. Maybe I have to log in again. Oh, no, I don't have to log in. Okay, good. So here you go. Here is the... Okay, so do you see those light shows, right? Here is an example of 2D motion, okay? You can see that is the path of a projectile. Because we have this flux of water, it draws in space the path of each droplet of water, which is very similar to that of a projectile, the one that we are going to study now. Okay, that's a very good illustration. And here you go, the displacement vector, final position minus initial position, right? Here you go. This cart here, this racing car, is moving in a two-dimensional space, and we have the initial position vector, final position vector, and that's the delta R. If you want to know the average velocity, you take this delta R, this vector delta R, divided by delta T. Okay. Here's the instantaneous velocity vector that will be always tangent to the path of the car. We covered that. Here's another one. This is one-dimensional motion. Okay, the guy was, let's see, the guy he started right in here, this rocket, and this plane, right? This is we call it spacecraft. This is spacecraft. He started with an initial velocity vector that relatively small and ends up with a final velocity vector that's much longer than this one. What does it mean? Vx minus v naught divided by delta t is going to have the same direction as this acceleration vector. Okay? So here's another motion along the y direction. And now if you combine the motion along the x direction with the motion along the y direction of this spacecraft, then you have something like that. The path that you see right in here. Okay? And then we are going to talk about projectile motion. Let me get my illustrations for projectile motion. Okay, so here you go. Since you are dealing with 2D motion, you will always need an X and Y axis, right? Here you go, X axis. This one goes right in here. Y axis. Play the movie, right? I like to do that. Here you go. Play the movie. Y axis. After the X and Y axis, we can now place the origin right here. X axis, Y axis, origin. We don't need that anymore. We don't need that anymore. Oh, wait a minute. Yeah. Okay, this one we keep. Okay. So what this coordinate axis is going to tell you? It's going to tell you the path of the particle. That is what it's going to tell you. Okay. When it comes to two-dimensional motion, yeah, we are going to have this X and Y graph, but then we are going to have other types of graph as well. We're going to have the X versus T graph. Okay, we're going to have the Y versus T graph. We're going to have the X component of the velocity versus T graph. Remember in 1D we had only X versus T, V versus T, and A versus T, but now we're going to have more, at least twice as much. Okay, and Vy versus T graph. Okay, AX versus T graph. AY versus T graph. We have 1, 2, 3, 4, 5, 6. 6 graphs only for whatever you have along the y-axis versus T. And one more that will depict the path of the projectile, the path of the particle, the Y versus X graph. And if it is 3D motion, then you're going to have three times more than 1D motion, right? Plus the X, Y, Z graph, right? 3, 6, 9, 10 graphs. Okay. So what type of graph may we have, right? Let's write down here. What types of graphs may we have in one? Do we have, right? Do we have in 1D, 2D, and 3D motion, right? So the answer here are the following, you know, 1D motion. Okay, so here you go. X versus T, 2 B versus T, 3 A versus T, right? And we have one more particle shown moving along the x-axis. 4 graphs. In the case of 2D motion, two-dimensional motion. In this case here would be the motion diagram, right? Motion diagram of the particle. Motion diagram of the particle along the x-axis. What about two-dimensional motion? Two-dimensional motion, we're going to have x versus t, y versus t, vx versus t, yeah, vy versus t, ax versus t, ay versus t. And we also have y versus x graph. Okay? Here, let's say it's 4. Here it's going to be 7, almost twice as much. And then for 3D motion, 3D motion, x versus t, y versus t, and what else? Z versus t. Are you getting the idea here? Are you getting the hang here? You know, Vx versus t, Vy versus t, we are going to have a z component for the velocity as well. And maybe we are going to have a z component for the acceleration. On the top of that, we are going to have, let's see, a path drawn along the x, y, z space, okay? X, Y, Z, or, and you already know how that's done, right? Or 3D space. And the most important, one of the most important situations that we study out there is the motion, projectile motion. Example of 2D motion. Projectile motion. Everything here is, oh wow, I didn't even notice it. Let's see if I can take this thing out. Okay, good. I got it. Oops. Okay. Projectile motion. Definition. Definition. What's the definition of projectile motion? Motion subjected only to the acceleration of gravity. Of gravity. That's the definition. And because, okay, there is no propulsion, the only acceleration of the particle will be the acceleration of gravity, okay? That's what projectile motion is all about. Okay, so here we go. So in the case, let's go ahead and set our axis, right? Let's play the movie again. Here you go. So we first draw the x-axis, then we draw the y-axis. First draw the x-axis, draw the y-axis. You're gonna put, let's put the origin here too, right? Notice that I'm putting the units between parentheses, right? place the unit, the origin here. And then let's not forget of our particle. Our particle now in this specific case is exactly here at the origin. Okay? Because the motion is that of a projectile, the projectile, whenever it starts to move, is going to be subjected only to the acceleration of gravity. And I'm gonna put it, and I'm going to emphasize here that this is the vector. Okay? Acceleration of the particle is equal to the acceleration of gravity, which, by the way, don't forget I'm writing down the vector here, which is equal to minus g y hat. I know it's minus because the axis, the y-axis is upwards. And this g here stands for 9.8 meters per second squared. Okay? What else do I need to describe my projectile motion? Okay? What I need the initial velocity vector and its direction. Okay? So let's make a better job here in the, yeah, here you go. See, initial velocity vector. So it's just like I'm propelling this particle, hitting it with a bat or firing it with a gun, okay? The initial velocity vector has a x component that's given by v naught cosine of theta, and it also has a y component given by v naught sine of theta. And once the particle is propelled, it's going to describe a path in the y-x space, in the y-x plane, okay? And as it moves along this plane, the vector velocity will change, okay? But not the acceleration vector. The acceleration vector will be the same throughout the path along the xy plane. This vector is going to be exactly equal to this vector, is going to be exactly equal to this vector. Okay? And how do you treat this type of situation, right? We already have the acceleration. We already have the initial velocity. I know the acceleration is going to be the same, doesn't going to change anything whatsoever. Okay, so here you go. Definition. Find the equations of motion. Define the equations of motion of the projectile. That's gonna be, let's say, our example, right? Find the equations of motion of our projectile, of the projectile. Motion should be only the acceleration. The acceleration of the particle will be the acceleration of gravity. Given an initial velocity vector. And when I mean initial velocity vector, I know the angle, direction, and magnitude are known, right? Initial velocity, let me get my initial velocity here. I can get this guy here, and then I change a little bit. V dot. Find the equation of motion of the projectile. And then solution. We use what we know. We use what we know. Because it's a projectile motion, we know for a fact what's going to be the direction of the acceleration vector. Right? Here you go. Here's my acceleration vector. My acceleration vector has a direction along the x-axis and has another direction along the y-axis. There is no acceleration along the x-axis, only along the y-axis. And this acceleration is minus g, or minus 9.82 meters per second square, right? Right in here. Right in here. Okay? Note C that the motion of the projectile along the y direction is that of uniform acceleration. Is a uniformly, let's see, along the y direction is uniformly accelerated, right? If it is uniformly accelerated, and I'm going to paste it here so it is more obvious. If it's uniformly accelerated, I'm going to go even one more step here. I'm going to put equal to AY, right? Oh, because AX is equal to 0. And I gotta change this one as well. Why? Y-axis, yeah, is uniformly accelerated. Consequently, we already know that the velocity along this direction will be linear with t, or, okay? So now we can write down the equation for the velocity along the y direction. Here you go. Oh, we don't need all I need is v sub y. Okay? And v naught y. Okay? Minus gt, right? Make sense? Notice that one, we're going to put two statements here so it's better organized, right? One, the motion along the x-axis is uniform because a sub x is equal to 0, right? However, the motion of the projectile along the y-axis is uniformly accelerated. Consequently, we already know. Consequently, we can write the equations for the velocity components as follows. And I'm going to put it here. Here you go. V along the x-axis. V along the x-axis is going to be equal to the initial velocity component of the velocity along the x-axis. Okay? And the velocity along the y-axis is going to be v naught y minus gt. And by the way, V naught x is going to be what? It's going to be V naught times cosine of theta. Nope. Oh. Jesus Christ. Let's see. This one here? Yeah, this one here. Okay, cosine of theta. Going back to the drawing, you'll see V naught cosine of theta. And V naught y is going to be V naught sine of theta. Okay. I know I was giving both the direction and the magnitude of the velocity vector, initial velocity vector, right? Let's follow. Similarly, along the x direction, the motion is uniform. Along the y direction, the motion is accelerated. Okay, so here you go. X is going to be given by x naught plus v naught x times t, right? What else? Plus half gt squared. Oh, no. Not this one. It's uniform motion along the x-axis, right? Don't let me do that. X naught is 0 because the particle is initially at the origin. V naught x is V naught cosine of theta. And we have the t. We'll put between parentheses here, so there's no doubt about that. Right? Equal to 0. V naught is equal to 0. But not V naught. But what about y? Y is going to be just like before. Y naught, uniformly accelerated motion, right? V naught y times t plus half a t squared. Okay? This term is also 0 because the particle was placed initially at the origin. I'm gonna get rid of this one here. Okay. V naught y is V naught sine of theta t. We still have the half. Okay, I'm gonna put the half here. I'm gonna put the way it is. We still have half, but the acceleration, hey, let's not forget, this is here a sub y, huh? Don't forget, a sub y is going to be minus g, right? And then finally, we get minus half gt squared. And those are the equations of motion. Okay. I didn't put them in vectors, right? I put them just in terms of their components. Here I put that in vector. If I put just write down just in terms of their components, it's going to be the following 1154. You're almost there, right? Here you go. A sub x equal to 0, right? A sub y equal to minus g. Like that. That's in terms of the components. Let's write that in terms of the vector, just like we did for the acceleration, right? Here you go. Vectorial notation. Instead of just the components, we are going to write that down now in terms of vectorial. Vx, Vy, right? Vx, I'm gonna copy and paste it here. I can erase everything else. I don't need that. Vx is V naught cosine theta in the x direction. Vy, I'm gonna put it between parentheses because it must multiply the y hat, okay? And we do the same here. Okay, instead of V, it's going to be R. Instead of Vx, it's going to be X. Instead of Vy, it's going to be Y. Okay? And copy and paste. I'm going to erase everything else. And I'm going to put this one here, parentheses here. This one doesn't need a parenthesis, but this one needs. Okay? For the first term, it's just one term multiplied by x hat. For the second term along the y direction is two terms. Okay? So I'll put now everything together just in vectorial notation. Vectorial notation again. Okay, here you go. Equations of motion. It's gonna be like that, right? It's going to be like that, but just the last term. I wanna put G. Okay, let's put G. And we do not need the meters per second square because the unit's already implicit in the G. Okay, here's the velocity vector. And here is the position vector. Almost done, 3 more minutes to go. Okay, so here you go. Equations of motion. Okay, equations of motion. These equations, we call it parametric equations. Parametric equations in terms of t, right? Equations of motion, parametric equations in t. That's what the equations of motion is all about. It's a parametric equation in terms of t. Okay. 11:58. Let's see if we have. Oh, we have 2 questions. I missed it here. Can we do an example from the book? Yes. Okay. 11:27. We will have more practice on this next week. We'll practice that. Don't forget this material here. It's not going to show up in the exam, right? I guess you meant Molly. I guess you meant the example from the book for chapters 1 and 2. Is that right, Molly?
I think it was what we were going over today.
Cool.
You were looking at the book, like example 3.2.
3.2. Okay. Okay, remind me next time because we ran out of time already, right? Example 3.2, let's see. 3.2, blah, 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 blah. No, example, must be this one here, example 2.
Yeah, I just want to see how we can relate these formulas with like actual numbers and doing a real example would be helpful.
Yeah, let's do that next time. Remind me the first hour when we meet for the lab, right? I'll do that. I'll do this example in class.
Okay.
Okay. this next week. Okay, so we can finish 12 noon now, right? I have office hours right now. And if you wanna hang around to ask any questions, I'll be available. Otherwise, see you on Wednesday.
Thank you.
Okay, see you.
Hi, Professor.
Hello.
Hi. I have a question about the lab.
Uh-huh.
How do you find the CL, the minimum and maximum?
Yeah, okay, so let's do that. Let me get let's see. Here. Syllabus and fall must be here. CL must be no. Here you go, confidence level. Okay. So here you go. How many data points do you have there in your graph? Do you remember? You gotta use this table, okay? You have to use this table to find out the upper and lower boundary. You have this table, right?
Yes.
Okay, good. So how many data points do you have in the graph?
In which graph?
Either one, the
Either?
first, second, or the third one. They all have the same number of data points.
I have 6.
Yeah, okay, so they all have 6. So you gotta concentrate on this row here of the table, okay?
Okay.
And then you gotta tell me what is your R square?
My R square is 0.9867.
9067.
It's 0.9867.
98. Okay, 0.9867. Okay, 0.9867 is between those two values here. Do you see that?
Yes.
Okay, so it's somewhere between here. So the CL of your experiment, is gonna be between those two values. Okay, see the CL right here? That's the role for the
Yes.
CL. So the minimum value, the lower bound, if not minimum value, but the lower bound of the CL is going to be 1 minus 10 to minus 4 and 1 minus 10 to minus 5. Okay?
Yes.
Lower bound, upper bound, mean, max, right?
Mm-hmm.
Did you get
So,
how you find it?
so you subtract?
What
Or
do you mean you subtract?
do you subtract the minimum from the maximum, or it
No.
just has the number in between?
No. Let's see. What group are you?
I'm group number 5.
Let's go to the spreadsheet of group number 5, right?
Okay.
Group number 5. Group number 5, right in here. Now, this value for R squared that you gave me is for which? For the ruler, for what?
This one is for, hold on, sorry. It's for the V caliper.
Vernier caliper. Vernier caliper. Okay,
Yeah.
so here you go. N is 6, right? Here's the regression equation. Regression equation that you have to write down. You have to write down the R squared is 0.98, right?
Yeah.
What else?
0.9867.
67. Okay. And now here you go. Let's put everything in format number. Okay. This one don't need all that decimal places. Okay, so here we found that 1 minus what? Let me 10 to minus 4, right? Yeah, 10 to minus 4.
Yeah.
That's the lower bound. That's the minimum value. 10 to minus 4. Okay? If you leave this way, look, if you leave this way, Excel is not going to do anything with it, and it's going to treat it as though it is a text, okay, not a number.
Yeah.
In order to ensure that Excel treats it as a number, you have to put an equal sign here in front of this value, okay?
Okay.
And then you get 0.9999, okay?
Okay.
That's for the CL min. And then
And it
CL
would
max,
be
yeah.
and
Go
it
ahead.
would be the same for all of them?
Yeah.
Or
Uh-huh.
oh, okay.
The CL is not going to be the same, necessarily the same. They're going to be different, but the
They're
procedure
gonna
is the same,
oh,
right?
okay, they're gonna be a little bit different because each of them have a different number at the end, right?
That's right. Has a different R square, right?
Mm-hmm.
The n is going to be the same, but the R square will be different.
Okay.
Okay. Okay, let's do the other one, right? The other one is 1
The
minus 10 to minus 5, right?
yes.
Okay, so we put the equal sign here. And then it calculates, it's giving us 1, but it's giving us 1 because we do not have enough decimal places there. If you add a decimal place, then we see that it's not 1, but it's close to 1, okay?
Mm-hmm.
And then
Yeah.
you repeat that for the ruler and the micrometer.
Okay. And then sorry, one last question. For the slope is what the y-axis sorry, what the it's when you get the equation, right? And you get what you get in front of the x
Yeah, so
is
let
the
me
slope.
see. Yeah, this slope is, here you go, you have the regression equation right in here, right?
Mm-hmm. Yeah.
That's the slope.
Yeah.
That's
Okay.
the slope, and this one is what? This one right in here is what?
That one is the y
Well,
intercept.
yeah, the intercept. Yeah, that's right.
Mm-hmm.
The intercept. That's the slope, and
So
that's the intercept.
when it says slope percentage difference, or what's that other thing? The slope percent difference.
Yeah, this one you're gonna log the slope, right?
Okay.
Okay, and when you log the slope, the spreadsheet is gonna calculate the percentage difference for you. Okay.
It didn't do it for that. So I have the same thing for the first one, but it didn't do it for my
Okay,
for
for your cell, right? It's possible
yeah.
that you erase the formula. It's possible that you erase the formula, okay?
Okay.
Maybe that's what happened, accidentally erased the formula. But the formula is this one here. See that? Do you see the formula there?
Hold on. Sorry. Okay, yeah, I see it.
Okay.
Mhm.
And then, oh, okay. So the form, do you have the formula there?
Yes.
Okay, so maybe the problem is that you didn't log the density here at the top. Did you log the density here at the top?
I did.
You did?
Yeah.
Okay.
I logged it at
But it's not calculating, is that right?
yeah.
Okay, you gotta share your screen with me, okay, so I can figure out what's going on.
Okay.
Did you upload your spreadsheet?
Not yet. I wanted to just fix this and then upload it.
Okay, I upload it now. Let's see if I can download it. It would be easier if I download it instead of you sharing the screen. Okay, upload it now. So 224, group number 5, right?
Yeah.
Is that the one here? No, that's me.
Sorry, just give me a second. Mm. You want me to upload it to Canvas?
No, upload it here to Google Drive.
Okay. Mm. Mm.